Hello everyone. It's our pleasure to have Julian here to share about his work with us. Today he'll be going to share about how to use like generative classifier to map out phase diagram of like quantum systems. And this is very interesting because like normally, at least for me, what I kind of use was typically discriminative type of classifiers. And today's like Julian will introduce us a new kind of classifiers that we can use for like studying quantum systems. Julian's like the floor is yours.
Thanks for the introduction and thanks for having me here today. Yeah, so today I'm going to talk to you about our recent work on mapping out phase diagrams with generative classifiers. So phase transitions are really ubiquitous in nature, and typically in our everyday lives we encounter them as changes between states of matter such as solid, liquid, and gas as a function of external conditions such as temperature and pressure. And within a phase of matter, a system usually has largely similar properties. So that means to characterize a new material or a new system, it really boils down to determining its phases and determining the transitions between these phases, so its phase boundaries. So mapping out phase diagrams is really a key task. And more generally, we can say that a system undergoes a phase transition when a qualitative change in its state happens as a function of a certain tuning parameter. And because, as you can see from the definition, this is quite general, and hence phase transitions occur in various different contexts and come in various different flavors. For example, there are transitions in the conductive properties of cuprates. So these are current candidates for high temperature superconductors. There are transitions in the entanglement properties of quantum circuits, for example, as a function of the probability of some measurements occurring or certain unitaries occurring, as well as transitions in the collective motion of active matter, or even in the behavior of artificial neural networks. But in general, this mapping out the phase diagram of a system is a really hard task, because the system state is typically very high dimensional, so it lives in a high dimensional space and is probabilistic in nature. So that means for a given set of the tuning parameter that characterizes our system, the system can be in various different states. And how physicists typically approach this problem is they try to find a suitable set of a few low dimensional quantities which capture the essence of each of the different phases in the system. And these low dimensional quantities are then typically called order parameters because they characterize the order that is present within each of the phases. So for example, even though water is a highly complex system, you can characterize the transition from liquid to gas by looking at its density. So if you plot the density as a function of temperature, it will show a sudden drop around the critical temperature. So in that case, the density serves as our order parameter. But this really requires a deeper knowledge of the system at hand and a physicist who identifies the density as a key quantity, so as an order parameter. Now, our goal is to map out phase diagrams autonomously from readily accessible data, so be it from simulation, numerical simulations, or experiments. So really replacing the physicist in that process. And we want to do this with minimal prior theoretical knowledge. So for example, we don't really want to rely on knowing the nature of the phases that are at play. And if we had such a generic tool, we could use it to identify unexplored phase transitions and potentially discover new phases of matter. And in this talk, I'm going to show you how we can do this by casting the problem of mapping out a phase diagram of a system as a classification task. And afterwards, we're going to solve this classification task using tools from machine learning. So how do we do this? So the scenario I have in mind is depicted here. So our system is characterized by two tuning parameters. gamma 1 and gamma 2. And at each point in this parameter space that we've sampled, such a point is denoted by a cross. And we sample the system here uniformly over a grid. And at each point in parameter space, we can measure the system. And the probability to observe the system in state X is given by P of X given gamma, where gamma denotes the point in parameter space with the red cross. And we can repeat such measurements many times for all of our sampled points to obtain for each point a data set E gamma containing different states of the system. So we can measure the system in different states because we have this probabilistic, because it is probabilistic in nature. And once we have all of these data sets, consider for a moment the scenario where we know the number of the phases that are present and their rough location. So what we have is we have a certain set of points which belong to, in that case, 3 groups. So we have 3 distinct phases. And these groups of points are called G1, G2, and G3. And all of the data within these points or drawn at these points are going to be given the label 1 for group 1, label 2 for group 2, and label 3 for group 3. And then we can ask a question. So given a sample X from the collection of our data sets that we have drawn, what group does this sample belong to? So what is the most likely group this sample belongs to? And that's equivalent to asking what is the probability distribution over all of the possible labels given the sample X. Because if we would know this probability distribution, we could make the best guess by just picking the label which maximizes this probability. And that's a classification task, because what we really do is we assign each possible sample X a corresponding group or a corresponding label. So that is the classification task we want to solve. So now let's assume for the moment that we have solved the task and we have access to P of label given X for all of the samples X within our data set, or in general within the state space. Then what we can do is we can compute an analog of an order parameter. So this, what I mean by that is we can take P label given X and we can sum over all possible states X within the state space and weight it by the probability of drawing X at a given point gamma. And then we obtain the probability of drawing a label at a given point in parameter space gamma. And these are pseudo order parameters. So these are analogs of order parameters, in the sense that if we consider our example from before, where we had 3 different phases, we can consider the 3 different quantities P of label 1 given gamma, P of label 2 given gamma, and P of label 3 given gamma. And if we draw these quantities as a function of gamma 1 and gamma 2, we arrive at these 2-dimensional maps. And these 2D maps, they will have high values close to the blue points, which are characteristic of the blue phase, so phase 1 in that case, or the orange points or the green points. So these are really analogs of order parameters, in the sense that these maps are reach a value close to 1 deep within the phase and drop down to 0 within the other phases. And we can, of course, in practice, we usually don't have access to the probability distribution P of X given gamma, but we need to estimate this expectation value. And so we replace it by a sample mean. So we just average P of label given X over all the data within the dataset E gamma. And then once we have these pseudo order parameters, we can also compute an analog of a susceptibility. And by susceptibility here, I loosely mean a derivative of some property of our system with respect to a tuning parameter. And so in that case, we consider these order parameter maps, p label given gamma. We compute their gradient. We take their L2 norm, and we sum over all different labels. And this quantity, that's going to be proportional to our so-called indicator of phase transitions. And that's an indicator in the sense that if we plot this quantity again over as a function of gamma 1 and gamma 2, this quantity will have high values at phase boundaries. So local maxima in this indicator function, so here shown in black, they will really highlight the phase boundaries and thus map out our phase diagram. And so we have seen that sort of the task of mapping out a phase diagram reduces to a classification task. So meaning it reduces to finding P of label given X. And once we have that quantity, we can compute an indicator function, and this indicator function reveals the phase diagram. Now, a crucial limitation of the approach I've shown you so far is that we need to know the rough location of all of the phases that are present within our system. But actually there exists an alternative labeling strategy and an alternative indicator that one can use, which does not require this. So what we do in that case is each sampled point in the parameter space is going to be assigned its own group. And so it's going to be assigned its own label. So here, this point on the top left, we assign it to group 1, and all of the data drawn at that point is going to be given the label 1. Orange point belongs to group 2, is going to be given the label 2, and so on, until we arrive at the last point, which belongs to group K. This is going to be given the label K. And then we can ask a question, namely we can ask, for a given X within all of these data sets, what is the most likely point, gamma, at which it was drawn? And so that is equivalent to asking the question, what is the probability distribution over the gammas, so all of the sampled points in parameter space given X? And that's just a different instance of the quantity I've shown you before, namely the probability distribution over the labels, where now the labels are given by the sampled points in parameter space. And once we have the quantity, we can compute an indicator, and this indicator looks a bit different now. So in this case, what we do is we first compute an estimator for gamma, so gamma hat, as a function given a sample X. And this is obtained by averaging gamma, or by weighting each gamma by the probability of X being drawn at that point. And then we can compute again a sort of 2D map, so gamma hat as a function of gamma by weighting gamma hat of each sample X by the probability of X being drawn at that point. And then these maps will have a similar property as the order parameter maps before, in the sense that one expects gamma hat as a function of gamma to vary most at phase transitions. So that means the highest variations should occur at the phase boundaries, and we can capture these variations by computing this indicator function I2. So this indicator function simply contains the directional derivatives, so derivatives of gamma I hat with respect to gamma I. And we also divide by the diagonal elements of the covariance matrix, so simply the variance of these estimators, because that's the natural scale of the fluctuations. So to get rid of the fluctuations, suppress them. So I guess intuitively it's clear why these indicators highlight phase transitions, but to give you a bit of more intuition and make it a bit more rigorous, one could show that all of these indicators, so in this case I1 and I2, and there are also more which fall into this category, they can be shown to be under approximators of the system's Fisher information. So in particular, one can show that I1 and I2, they lower bound the square root of the trace of the system's Fisher information matrix F. So the Fisher information matrix, or entries in the Fisher information matrix, they measure how quickly the probability distribution, so in that case P of x given gamma, changes with respect to the tuning parameter gamma. So an entry Fij of this Fisher information matrix contains the derivative of the log of P of x given gamma with respect to gamma I, gamma j, and we weight it by the probability of drawing a particular sample at that point. Now, the Fisher information is a quantity from statistics, and per se has nothing to do with physics. But if we plug in probability distributions underlying the measurement statistics of physical systems, then we see that actually the Fisher information highlights thermal and quantum phase transitions. And this has been known for a while. So for example, if we consider the Fisher information, and here I just mean its diagonal entries, of classical equilibrium systems, so systems governed by a Boltzmann distribution, classical systems, then the Fisher information, so these diagonal entries, they will be related to second derivatives of the free energy. So where A is the Helmholtz free energy. And so in that sense, the Fisher information can pick up on non-analyticities in the free energy and therefore signal first and second order phase transitions.
Sorry, I have a question over here.
Yep.
How about the off diagonal terms? Like, do you is there any kind of physical quantity that could be kind of explained by the off diagonal of the Fisher informations, or like we can only just look at the diagonals of the Fisher information?
So that you can look at the off diagonals, but in terms of detecting phase transitions, you can argue that only the diagonals are relevant, in the sense that you can always choose an appropriate basis such that your Fisher information matrix is diagonal. The off diagonal matrix, they correspond to sort of changes in your distribution when you change both parameters, right? Which can be something like, for example, let's say you have two parameters like temperature and the magnetic field, then you would vary both of them at the same time.
I see. Okay.
Yeah.
Okay, thanks.
So this should provide you some intuition on why these indicators can highlight phase transitions. Because in the end, what we do is we compute these indicators, and they are deeply related to Fisher information. So the indicators are a way of approximating the Fisher information in a data-driven way. So now coming back to our goal of mapping out phase diagrams from data, we've seen that we can cast it as a classification task. And to solve this classification task, we need to know P of label given X. So that's what it all boils down to. And so far, we've assumed that we have access to that quantity, but usually we don't. So usually we just have access to data, and we need to model it somehow. And there are two, in the following, I'm going to present two distinct approaches of doing that. And this is a discriminative approach and a generative approach. So in a discriminative approach to solving classification tasks, you would model the probability of the labels given X directly. So what I mean by that is usually what you would do is you would parameterize this object with a neural network, and you would train it to reproduce some known labels. So this is similar to when you want to classify, for example, cats and dogs, images of cats and dogs. But here we want to classify or distinguish between different points in parameter space. And in the following, I'm going to denote approximate quantities, so these models, with a tilde on top. And what I mean by training this neural network, so here I'm depicting a feed-forward neural network, but if you know more about your system, you could also use a convolutional neural network or some other architecture. And what I mean by training it is we minimize cross entropy loss via gradient descent or some variant of it. But there exists another approach, which is more indirect, and this is the so-called generative approach. And in that case, we explicitly construct models for P of X given a label and the probability distribution of a label itself. And via Bayes' theorem, we can then obtain the probability distribution of the labels given X. So that's the the quantity we care about in the end. And that's in the end our classifier. And this approach is called generative because P of X given a label tells us how the data with a given label is generated. So if I pick a certain label, that tells us how we can generate samples which are representative of that label. And why do we make this detour? So why do we model these quantities? Well, it turns out that in the special case of phase classification tasks, the probability of obtaining a label given X is proportional to the sum of the probabilities of obtaining X at a given point gamma, where we sum over all of the points gamma belonging to the group of that particular label. So these will be all of the colored points within a certain set. So what does that mean? So that means that in order to obtain the quantity we care about in the end, this probability distribution of the labels given X, our classifier, we just have to find a model for the probability distribution of X given gamma. And remember that this is the probability distribution that characterizes our measurement. So if we if we have a certain point in parameter space, this tells us how we generate samples from our system. And in physics, that is usually very well characterized, and we have quite a good idea of how this object looks like. So for example, in the case of classical equilibrium systems, these will be Boltzmann distributions. And in the case of quantum systems, these will take the form of a Born's rule, where rho is the corresponding density matrix, which is parameterized by gamma, and pi x is a POVM element. So now we have seen these two approaches. One is this discriminative approach, where we model P of label given X directly. And one is the generative approach, where we model P of X given gamma. And these are two distinct approaches. And in general, it's unclear which approach is better in terms of efficiency. And this depends on the problem specifics. So namely the desired accuracy we want to reach of our indicator, the data we have available, what kind of system information we have. So do we know something about the Hamiltonian or the structure of these probability distributions and the available computational budget. But in this talk, I'm going to convince you that there's a large class of settings where the generative approach has an advantage over the discriminative approach. And namely, in numerical investigations, what often happens is that we have access to a description of our system in terms of generative models, P tilde of X given gamma, and they act as a data source in the sense that all of the data we draw, the data sets we construct, we really draw them by simulating our system using these generative models. So examples of that are mean field descriptions, autoregressive networks, which are used, for example, to model both classical and quantum lattice systems, normalizing flows, which are typically used to model continuous variable systems, as well as tensor networks. So all of these are examples of generative models with an explicit tractable density. And why is this useful? Well, let's say we have access to such a generative model underlying our data. If we use the discriminative approach, our classifier is learned iteratively from data. We just optimize, train our neural network based on our data, and we sort of disregard these generative models. We don't use them. Whereas the generative approach can directly use these generative models to construct a classifier, and it can bypass this iterative training process, which in general is going to make it computationally more efficient. So that is the key advantage behind this generative approach. So in the following, I'm going to consider two specific examples where this generative approach is advantageous in comparison to the discriminative one. So the first example belongs to the class of classical equilibrium systems. So what I imagine is that we have a system described by a Boltzmann distribution, and the Hamiltonian curly H takes on a specific form. Namely, it's a linear combination of sort of generalized coordinates, capital Xi, which couple linearly to the tuning parameters, gamma I. And we have d of them. And if you have a Hamiltonian of that form, then the Boltzmann distribution belongs to an exponential family. And that means that these capital X, all of these, the set of these capital X, they are a minimal sufficient statistic for gamma, meaning that if we map the state of the system X to capital X, so we just consider these fewer collective variables, then this corresponds to an optimal lossless compression with respect to gamma, in the sense that by performing this map, by performing this dimensionality reduction, we don't lose any information about gamma. And this is important because based on that, one can show that in order to map out phase diagrams by computing indicator functions, it really suffices to model P of capital X given gamma, so the probability distribution over these collective variables, instead of the full probability distribution, which is generally inaccessible due to the fact that X can be very high dimensional. So this is the same reason why we cannot access the partition function in general. And as I said, usually this capital X is lower dimensional, so the dimension of X is d, and this can be independent of the system size, and that enables simple non-parametric modeling approaches. So simple approaches for obtaining models for this guy here, P of capital X given gamma. In particular, what we can do is we can draw configurations X from a Boltzmann distribution, for example, via Markov chain Monte Carlo. And then we can construct an empirical distribution, P tilde, of the collective variables using histogram binning. And because capital X is low dimensional, we only need very few data points to get good statistics. So we can go to very large system sizes, and this still works. And then based on these models P tilde for capital X given gamma, we can construct a generative classifier. So we can construct the probability of our labels given X, and based on that, we can compute an indicator of phase transitions. So as a concrete example, we can consider the two-dimensional anisotropic Ising model. So we have a two-dimensional square lattice of classical spins. So the spin variables are denoted by sigma, and they take on the values of +1 or -1. And the system is described by the following Hamiltonian. So we have nearest neighbor coupling. So sigma spins between nearest neighbors couple, and we have potentially different couplings either in the X direction and in the Y direction. And so these couplings, strengths Jx and Jy, they are our tuning parameters, gamma in that case. And we consider the system to be at thermal equilibrium. So the system states are distributed via a Boltzmann distribution. And on the bottom left, you see the reference phase diagram. So we have sort of two phases. We have a paramagnetic phase, so a disordered phase for low values of Jx and Jy, and four distinct orderings, so which all belong to an ordered phase. And here you see depicted, you see the ordering of the particular ground state that dominates in that region. Now we can draw spin configurations from the Boltzmann distribution via Markov chain Monte Carlo, compute the sufficient statistic, the minimal sufficient statistic, these collective coordinates, and do histogram binning to obtain a generative model. And based on these generative models, we can compute these indicator maps. So here you see the indicator map I1 tilde and I2 tilde. And the tilde here just denotes the fact that, again, we are doing this based on samples, so we have a certain approximation error. Whereas I1 would correspond to the exact quantity we would reach in the infinite data limit. So here, I1 tilde, on top of this map, you also see the colored crosses, and these denote the training point. So remember that in this case, for this first approach, we need to know the rough location of all of the phases that are present. And here I've just picked a single point in each of the 5 regions. And you see that the indicator map, the local maxima in this indicator are close to the true phase boundary, which is shown in red. And if we sort of move these crosses closer to the true phase boundary, so we basically give more information about the location of the phases, these indicator curves would approach the true phase boundary. So this is one of the limitations of this first approach, and it can be resolved by the second one, which doesn't require any information about the location of the phases, I2. So I2 tilde, if we look at it again, local maxima in this indicator map correctly highlights the phase boundaries. So in terms of the computational advantage of the generative approach over the discriminative approach, let us assume that we have a trained feed-forward neural network for the discriminative approach. And let's just pick the neural network of a minimal size. So it just contains a single hidden layer and a single node. And in that case, one can do some calculations and find out that the speed up in the indicator computation of I1 or I2 of the generative approach compared to the discriminative approach is on the order of 35 or 3. But of course, this is a very small neural network and will just lead to approximations of I1 and I2 of very poor quality. So if in practice, one will need to use a larger neural network. So here I've picked another example. For example, if you take a network with 5 hidden layers with 1024 nodes each, which would be more realistic, we will get speed ups of order 10 to the 3 or 10 to the 2. And just note that these are minimal speedups in the sense that to compute these, we already assume that we have a trained discriminative model. So the training itself is, the training time itself is neglected. I mean, so we neglect the fact that we have this iterative process, but we just assume that we have a trained neural network. Because the generative approach utilizes the generative model, which we already have at hand. So any training that we have to do, this is just overhead for the discriminative approach and makes it even worse. So as another example, let's consider a quantum setting. So we consider a quantum ground state system. In this case, it's a one-dimensional chain of qubits described by the following cluster Ising-Hamiltonian. So this cluster Ising-Hamiltonian contains 3-body interactions. It contains the coupling to an external field with strength H and nearest neighbor coupling with strength J. So we have these 2 tuning parameters, H and J. And you see a reference phase diagram on the bottom left. It contains 3 different phases. So on the bottom, we have an antiferromagnetic phase. We have in the middle a symmetry protected topological phase, and we have a paramagnetic phase on top. Now we can get matrix product state representations of the ground state of that system via DMRG, and we form a tomographically complete set of measurements. So in this case, we consider Pauli 6 POVMs. And based on this MPS representation, we have direct access to the measurement statistics underlying the system. So we have all of the generative models we need to compute our indicators I1 and I2 in a generative way. So here you see again the corresponding indicator maps, I1 tilde, I2 tilde. And in that case, both of them nicely highlight the phase boundary and thus map out its phase diagram. Now, in terms of computational costs, so here we did a bit more of a sophisticated analysis. So what you see here is the approximation error. So the difference between I tilde and I, where I tilde is the indicator computed with a finite data set, whereas I is the indicator obtaining the infinite data limit. So in that case, we obtain it via exact diagonalization. This on the y-axis, we have this approximation error, so it's just a root mean square deviation. And on the x-axis, we have the computation time needed to compute the indicator, either with a generative approach, which is shown in black, or the discriminative approach, which is shown in blue. And we'll consider this for both I1 on the left, so the first approach, first labeling scheme, and I2, the second labeling scheme on the right. And in both cases, both for the generative approach and the discriminative approach, we consider multiple runs. So in the generative approach, you see we also have multiple lines, multiple black lines, and they correspond to different data set sizes. So that's why we can have different computation times. So that just corresponds to making the data set larger and larger. And in the discriminative approach, we use a simple feed-forward neural network. And there we also vary the neural network sizes, we vary the learning rates and the number of training epochs. So the blue lines really correspond to different runs with different dataset sizes, as well as neural network hyperparameters. And what you can see is that, especially if we want to go to low errors, so good approximations of our indicator in that region, in these two regions, and the generative approach becomes more advantageous. And another thing to note is that in general, because the generative approach doesn't have any hyperparameters in it, we can get much more nicer improvements over time. So as we increase the dataset size compared to the discriminative approach, where we have to potentially tune hyperparameters. Right, so that brings me to the end. So I've shown you a generic framework for mapping out phase diagrams in an automated fashion. And this could enable the discovery of new phases of matter. And I've shown you that this boils down to solving a classification task based on which we can compute an indicator. And this classification task can be solved in two distinct ways. A discriminative approach, which has been sort of the most popular so far in literature, as well as a generative approach, which is the main proposal of our new work. And as an outlook, we always look for applying our methods to other systems, in particular experimental data. And we are currently working on sort of fleshing out this comparison in terms of resources between the discriminative approach and generative approach in a more general setting. So here's the link to all of the relevant works, and we also have an implementation of these methods on GitHub if you want to check that out. Thanks.
Cool. Thanks, Julian, for the very informative talks. For the audience, if you have any questions, feel free to unmute yourself or type a question in chat, and I could help you ask it. In the meantime, maybe I could ask a couple of questions over here. I'm just like wondering how robust is the generative model's approach to noise, for example. Because over here you just consider just perfect systems, right? But once you add in some for example the experimental noise, all the short noise and stuff, how do you think it performance will be affected by the noise? Whether the is noise robustness or between discriminative and generative models, how does that compare? I know it's beyond the kind of scope of your studies. I'm just wondering whether you have any intuition on that.
Right. So just as a start, I would say I would distinguish between two settings. So one is the setting where we work in numerical simulations. Mm-hmm. So there, if we have a generative model based on which we draw the data, I would say both approaches are affected by noise in the same fashion. So let's assume we sort of approximate our ground state with a variational procedure, right? Let's say we use an MPS approximation of DMRG. We have a certain error on that. And that error will be error of this ground state will be the same because we use the same data for both calculations. Now, in case of the experimental data, I would argue it could be it could work in a similar way. Obviously it could depend on the specifics, so it's hard to say whether one approach will be more susceptible than the other, because one can do sophisticated things in this modeling stage, right? So you could try to build in noise resilience within the architecture, be it in the discriminative model or the generative model. So because there are completely different types of models, right? So the discriminative model could be a feed-forward neural network, could be a convolutional neural network, whereas the generative model is something like an autoregressive network, a transformer. It's hard to compare them on equal footing, right? Because if we consider different architectures, they might behave differently. Yeah.
I see. Okay. And another question that I have, right, as in, okay, so this what I'm a bit unsure of is like in unsupervised machine learning, basically we also consider like generative approach, right? Like how does that differ or like similar to the approach that you consider this like the things that I hadn't really understood fully, like the difference between these two methods, or maybe they are the same, yeah.
Right.
Like for example, I could have a bunch of data point and then I didn't know about the labels, and then now I just like use some set clustering algorithm to help me cluster that, and then how this kind of unsupervised machine learning algorithms differs compared to the generative approach that you have.
Right. I would say
yeah, I'm not sure whether the question that I asked is valid, because like typically that's why I never kind of encountered this before, because like typically when we speak of generative modeling, we would for me I normally just encounter it in unsupervised machine learning manners, right? And then yeah.
All right, I think like why people sometimes refer to generative modeling as unsupervised is because in that case they really assume in my talk I always talked about P of X given gamma, right? Or P of X given some label, so to speak. And if we consider the label to be fixed, then you can just approach this task in an unsupervised way. It's just about finding the density probability distribution underlying your data. And that's why, and this is unsupervised, right? So imagine like you have a set of images of cats. You can just model the distribution of those cats without having any labels, right? Because they're all cats and you're just like worried about generating new cats. And that task, I would say, is unsupervised. But as soon as you sort of introduce a label, so you want to condition on a certain property. So for example, you want to sort of condition on the type of cat you want to generate. Then, yeah, that label needs to come from somewhere. Maybe you have some smart technique to figure out the label again without knowing it beforehand. But in general, you could approach it by in a supervised way then, by providing the labels.
I see. Okay.
Hi, can I just ask a question? So I probably don't fully understand some things here and there, but I'm just curious. At some point you mentioned that already here you do mention that there is discovery of new phases matter. How crucial is it that you actually sample a point from all the phases? I can imagine that if you whichever procedure, whichever scheme of sampling that you do, let's say the Monte Carlo Markov chain, right? You could basically sample all like points. You could miss a point in some other phase. Let's say the phase space is really small, for example. So then in that case, will it actually know that from this training, will it actually know that there is this this phase in this very tiny with this very tiny phase space?
Right. So by just to confirm, by tiny phase space.
So for instance, I think like one of these diagrams, maybe
Yeah.
let's say we could look at like maybe the classical example, for example, maybe on slide.
So the Ising
one, yeah, or the quantum. I think it's similar in the sense that, yeah. So for example, right? So I'm not sure if I understood this, like the middle figure here is you have 5 crosses. Is these the 5 sample points, for example?
Right. So these are what I do here is for this first labeling scheme, for this first approach of mapping out phase diagrams from data, I need to know the number of the phases. So in that case, sort of we have 5 different phases, quote unquote, 1 or a disordered one and 4 ordered ones. And I need to know their rough location, meaning from this grid of sampled points, for some of them, I need to know which phase they belong to. And you're right in a sense that I think technically you need to know you need to have a point in each of the phases. That gives you the best guarantees of success. But actually, you can detect sort of different phases. So let's say I would leave out the green point, then you would still be able to obtain the phase boundary to this top left region. But the fact that
because of the pink cross in the middle, right?
Exactly. Because imagine because what you do is in essence, for each of the crosses, that gives you a phase, and that gives you sort of an order parameter map. And the indicator computes changes in the order parameter map. And let's say if we pick the boundary from the top left region to the middle one, that involves the order parameter map in green and the pink one. And you sum up the changes in both. But obviously you can just look at the change in one, and that will already suffice.
Right. Okay. So I guess as long as you have you have sampled the adjacent phases, like along across the phase boundary, then you still can sort of in this way sort of discover new phases.
Exactly.
Okay. So what might sorry, go on.
Yeah, no, that's correct. So what might happen is, for example, let's say in this picture, if you had just sampled, let's say, the top phase, then you might miss the transition between the symmetry protected and the antiferromagnetic one, right?
Yeah, that's right.
Yeah.
So is there a way to guarantee that you would sample, is there sort of a sampling scheme that will ensure that you sort of cover at least a point in each of the different phases? Or it's hard to do a priori?
Yeah, so this is, as I would say, this is like one of the main drawbacks of this first approach that I am shown. Because as you say, ultimately, sort of the main advantage or the main goal of these methods is to detect new phases. And then you have this caveat that, well, actually, you need to know the number of the phases beforehand and their rough location. The methods still bring you value. So this first method, because it might be the case that you don't know the phase boundary exactly, right? Or you can sort of refine your guess by using these methods. Yeah. But these crosses, the location of these crosses is really something that needs to come from outside. Like this needs to come from some prior knowledge. For example, what occurs often is, imagine a scenario where, for example, in this case, we could consider the line h equals 0. So that's what we've done here. So if we set h equals 0, consider that line, then the model is actually solvable analytically. And so then you can pick these points and sort of say, well, that is a special line, and there we know the phases because we can solve the model analytically. Away from h equals 0, so for non-zero h, we don't know it. And there, the phase boundaries are provided by our method. So this is one scenario which commonly arises, is that you have special points or special lines in parameter space where you know a lot about the model because it simplifies in some way. And there you can put the points, and there you can characterize all of the phases, and then you sort of extrapolate.
I see. Yeah, that's very interesting. Yeah, thanks.
Yeah, very good question. Thanks.
Okay, cool. I think like we didn't have any more questions for the audience, so maybe you can like close the seminar. And I guess like if like the audience have any questions or people watching the video from YouTube have any questions, like they could always just approach you to ask more questions about your work. Yeah. So
Yeah, for sure.
we thanks again Julian for that very interesting talk, and thank you everyone for attending the seminar. See you guys. Bye bye.
Thanks a lot.